Am I audible? Am I audible?
Yes, sir.
Okay. So up to last lecture, we have started this diffraction. So what is diffraction, Krishna? What does diffraction of
So
light mean?
bending of light around small obstacles.
The bending of light is basically diffraction, and we have also discussed this first single slit experiment. So this is the source of light. The light rays coming from this source bends, and due to bending, the light rays reach over this point. When the light waves reaching over this point from the different parts of the bent wavefront superimpose, you get some bright or dark fringes. Bright fringes means light wave and light wave gets added up. Dark fringe means light and light will cancel out each other. We have discussed that over this point, you will get a central maxima, or this is known as central bright fringe. Over this point, you will get some fringe. This could be a bright fringe or a dark fringe. Now you have to calculate the conditions for which point P will be a bright spot or a maxima, and point P will be a dark spot or a minima. Maxima means, I'm repeating again, wave and wave will get added up. Dark means waves will subtract from wave. We have discussed these type of things in interferences much detail. Now to decide whether this point will have a maxima or a minima, consider these 2 points, point A and point B. The light waves starting from point A and point B will reach at point B. So they will cover different paths. It's very clear from the figure that the waves starting from point A will cover a comparative smaller part as compared to the light wave reaching point P from this point B. So the rays traveling from B to P will cover a larger path as compared to waves traveling from A to P now. So there is a phase difference between them, right? So there should be a path difference between them. If I drop a perpendicular here, then this distance AN will be, this distance BN will be the path difference between waves reaching point P from point A and point B respectively. This is the path difference. BN is the path difference. BN is the path difference. To calculate this path difference, what we can do is we can just use this triangle A and B. It's a right angle triangle. If this angle is theta, this is theta, this angle is theta, you can call that this angle is also theta. To get the value of Bn, what we can do is we can apply some basic trigonometry in triangle ABN. See why this is theta. This is theta. This angle will be 90 minus theta. This whole is 90 degrees, so this will be theta. Now in triangle ABN, you know that this AB is equal to the slit with A. You just need Bn. So what is cos theta in this triangle? The value of cos theta here. Meenakshi. Meenakshi, what is the value of cos theta in triangle A and B?
Sir, A by Bn.
No, cos theta will be Bn. Sorry, yes. Not cos theta. We need perpendicular. So which trigonometric ratio will be suitable? Cos or sine? Sine, I think, na?
Sine.
Sine. So in triangle A and B, what would be sine theta? Sine theta would be the ratio of
Bn.
Bn and AB.
Yes. Sir.
So sine theta is Bn by AB. And how much is AB? AB is equal to A. So you can write that Bn is equal to A sine theta. This is the triangle, A and B triangle. This is your part difference, A sine theta.
Sir, Bn by AB or Bn by A?
Bn by AB, and AB is equal to A. Bn by AB. Bn by AB. So it's Bn divided by A. So you can write that Bn is equal to A sine theta. That's it. So this is the part difference.
Sir, can you show the diagram once again?
Yes, I'm showing the diagram. And see, this separation here is the linear separation of the nth fringe. Yn is the linear fringe separation. Linear separation from the central maxima, the separation of this nth fringe is Yn. This is the linear fringe separation. And this theta here is known as the angular fringe separation. So this Yn and theta can be related. Theta is the angular part of Yn. Okay, just note it down. Then we'll start the next part of the calculation. Note it down, please. Can I scroll it if you all you have drawn this thing?
No, sir, wait.
No, 1 minute, sir.
Although we have discussed this particular diagram in the last class. If anyone have issue in this diagram, I can repeat it again. Because entire diffraction depends upon this diagram only.
So you can just summarize it again.
Yes. See, this is the single slit. This one. This is the slit. An opening small. The size of the opening is a. This is source of light. Light waves coming from this source is passing through a convex lens. The light source is at the focus of the convex lens. When light rays from the source passes through the convex lens, they becomes parallel. When this parallel rays passes through this slit, then it gets diffracted. Diffracted means it bends at different angles. So some waves will go straight without any bending. These one, there's no bending in these waves. Then they converge over a point, and this point is known as central bright fringe or central maximum. Some will bend at some angle theta, and they converge over this point. We call this as nth fringe, or we can say simply nth maximum. Fringe, or you can say nth maximum. This theta here decides the extent of bending. The greater the value of theta, greater will the bending, right? So naturally, this, if light rays are going like this, then they bend here and they bend here. So greater the bending, greater would be the angle value of angle theta. So we call this theta as sometimes the angular fringe separation. And this Yn is the separation from the central bright fringe to some point P. Over this point, these waves which bend at a particular angle theta will converge, and you will get a maxima or a minima over this point. The linear separation between O and P is Yn. The separation between the single slit and here it's capital. The simple thing, light waves are coming through the slit, they bend. Due to bending, they overlap with each other, and when they overlap, they form some sort of spots, bright spot or a dark spot. Is it clear?
So,
Mhm.
so we can have more than one nth maximum. So because
Yes. Oh, all over the screen you will have some maxima. First maxima, second maxima, third maxima, fourth maxima.
Okay. Yes, sir, got it.
So it's like it's a this pattern. Huh? This is central. Then you have first maxima, second maxima, third maxima, fourth maxima, and so on.
Okay.
This is like actual experiment. Meher, Nabil. Nabil, is it clear?
Yes, sir.
Bhishma?
Yes, sir.
Yes, Umar. See, these waves, these are the incident waves. Huh? When these waves passes through the slit, they bend at different angle. So if I show here, these waves, which when they pass through the slit, they bend at different angles. Some does not bend, they pass straight. Some will bend at some angle, some other will bend at some angle. And these waves are known as diffracted waves. These are the diffracted. When these diffracted waves passes through this convex lens, they converge and they form some spots on the screen. Spots like these types of spots. This is the central bright spot. This is the central bright spot, which we call central bright fringe or central maxima. Then you get secondary maxima and secondary minima. Maxima means light wave will get added up with the light wave, like these types of bright spots. Minima means light waves and light waves will cancel each other. This one, this one, this one. Haji, is it clear?
Yes, sir. Yes, sir. Clear.
Just tell me if you have written or we have already invested time.
Answer.
Okay. So for calculations, two distances are very important. First one is the part difference. This Bn is the part difference. You can note down the expression of Bn from here. Bn is A sine theta. Note it down. A is the slit width. And theta is the angular fringe separation. And Bn is the part difference. Yes, see the waves. If anyone else have doubt regarding the part difference, the waves reaching point P are coming from point A and point B. The waves reaching point P from A will cover a shorter path. It's a geometrical path. See, the waves reaching point P from B will cover a comparative larger path. So you know that BP, it's very clear from the diagram that BP is greater than AN. So the difference between BP and AP will be the part difference. For that difference, what we do, we drop a perpendicular over here. The perpendicular, the name of the perpendicular is N. After dropping this perpendicular, the AP and NP is equal. This perpendicular divide this line, this wave, this line particular into two parts. This NP is exactly equal to AP. The leftover, this is the extra part, and this is what we call part.
Sir.
Mhm.
Sir, after we are dropping a perpendicular,
Mhm.
the point, I mean, the waves from A and B will have the same origin then.
The waves after dropping the perpendicular.
Yes, sir.
No, they have the waves are coming from A and B. These are two different points, right? We are just calculating the difference in path. See, if you have two lines, huh? This is one line and this is, let's say, another line. Okay, they are unequal. Let's call this as line 1 and let's call this as line 2. I ask you to cut a portion from line 2 which is equal to line 1. What you will do? Cut a portion of line 2 which is equal to line 1. What you will
Sir,
do?
I will draw perpendicular from the
You
end
drop
point
a
of the
perpendicular. Okay. So this portion and this portion becomes equal. And what about this? This is the extra portion?
extra portion, the
If
part difference.
Yeah, that's the part difference. So this
Okay, sir.
extra portion is the part difference. Okay, so once you have the part difference, Pn is a sine theta. The next thing is, the next important relation is distance is this yn. We have to relate this yn with this theta. So if you look at this triangle, COP triangle very carefully, this point C, this point O, and this point C. How much is tan theta? Nabil, how much is tan theta in this triangle? OCOP. What is the value of tan theta here? Nabil Ahmed.
91 is it?
Sorry? What is tan theta, Nabil? Nabil, you're not audible. Saifullah, what's the value of tan theta here?
Which triangle, sir?
By OC.
Triangle COP.
Sir, OP by OC.
The tan theta will be perpendicular upon base. COP. So it's OP by CO. So yn is linear separation. So tan theta is yn divided by d, or I can write this as tan theta is. What is yn? This is OP and base is CO. So it's OP by CO. OP divided by CO. How much is OP? If you look at this diagram, OP is yn and how much is CO is equal to d. So you can write this as it's yn divided by C. See, this n in the subscript here simply shows that this is for a particular fringe, nth fringe. If it is for first fringe, then we will put a subscript 1 here. For second fringe, we will put a subscript 2 here. I didn't write n here just not to make this diagram very complicated. Now, already there are many terms in the diagram. So just to keep it very simple, I don't write n in the subscript, but then I introduce n in the subscript. N means for a particular fringe. If it is second fringe, then you will write 2 here. So I'm not multiplying this with n. This n is in the subscript only. So this is tan theta, which is yn by d. So you can write that yn is d sine theta. So these are important relations here. One,
Sir,
part
why are we-
difference.
Sir, why are we taking tan theta?
It's because the base is known, d is known, and we have to, and this yn is what we are supposed to calculate. So tan theta is the best bet, right? If you take sine theta, then you need this hypotenuse. It's not known. If you take cos theta, then this yn will not come in the formula of cos theta. So best available option is tan theta. So these are the important relations. One is part difference, which is a sine theta. Then the relation between yn and theta n. What is yn? What is theta n? Noah? Noah. What is theta
Sir,
n here?
the angular separation for the
And what is
end.
yn?
So the linear separation of the
Linear.
end.
Linear. So theta is angular and yn is the linear separation. Okay. Now, we can also use small angle approximations. Small angle approximations means if theta is very small, then you can write sine theta as theta and you can write tan theta as theta. This is true only if the angle is small. So for small angles, you can write sine theta n equal to theta n and tan theta n equal to theta n. So in both the expressions here, instead of sine theta n, you can write theta n only. Here also, instead of tan theta n, you can write theta n only. So the part difference and your linear separation will become this. But remember, this is valid if your theta is a small angle. And also your theta should be in radian. Don't use this one if your theta is in degree. Theta should be in radian.
Sir, can you scroll a bit up?
Yes. More?
No, that's fine.
It's okay. I'm coming to it. Just first let me finish this talk this time. So this is Bn is a theta n and yn is d theta n. Note it down now.
Yeah, but if the theta is given in degrees, so I cannot use.
And convert it in radian. Right? Convert it in radian, then use the approximation.
Sir, in all case or only in small angle approximation?
In small angle approximation. See, like, I mean, if you have sine of 0.1 degree, then you can't write it as 0.1. Okay, to write it as 0.1, it should be in radian. This is what I'm saying. For small angle approximation, your angle should be in radian.
So that statement,
Mhm.
with the diagram, it is if theta n is on angular separation, right?
Yes, if theta n is angular separation and n is in subscript, so we are not multiplying theta and n. Theta n means
Okay, sir. Okay.
theta for the nth maximum or nth minimum. Omar, our first prime objective is to get the expression of part difference and the relation between angular separation and linear separation. And then we will write the conditions for which any particular fringe could be a bright fringe or the fringe could be a dark fringe. Means you will get a bright spot or a dark spot. So you need the conditions for which you will get this type of bright spot or this type of this type of dark spot. That's the prime objective. to derive conditions for which you get these types of slope. Okay, can I scroll it now? If you all have written.
No, sir, I'm
Yes.
writing.
Sure. Arpit, clear? Muneeb?
Yes, sir.
Yashika, what topic are you doing in school right now?
Sir, we're doing dual nature of light.
So you have finished optics, both ray and wave.
Yes, sir, we're finished both.
Just tell me once you have written else. Can I scroll it now? Nah. Yes, no.
Yes, sir.
Okay. So these are the primary relations that we'll be using. The next thing is we need conditions for which a particular fringe is a dark fringe. So ignore this thing for the time being. Don't just ignore this term for the time. We need conditions for which you get a bright fringe or a dark fringe. Or in diffraction, we usually don't use the word fringe. Instead of fringe, we use secondary minima or we use secondary maxima. Secondary minima is the term for the dark fringe and secondary maxima is the term for the bright fringe. So we need conditions for secondary minima. Now, the next thing is, unlike interference, you don't have to derive these conditions. So in interference, we do full calculation in what conditions you get a bright fringe, you get a dark fringe. But in diffraction, you are not expected to derive these conditions. You will simply have to memorize that part difference, A sine theta will be equal to n lambda. This is for a secondary minima. And once you have the part difference, you can calculate everything, angular separation, linear separation, everything. So this is the condition that you have to memorize. Like I can't derive it. That part difference A sine theta is n lambda. That's it. N is the number of minima. Like for first minima, your n will be 1. For second minima, your n will be 2 and so on. The value of n will change. If I use small angle approximation, then instead of this sine theta n, what we can write instead of sine theta n, if you use small angle approximation only?
So
A
theta.
theta.
Theta. So instead of sine theta n, I can write just theta n. So theta n will be n lambda by a. I'm dividing this n lambda by a here. So this we can write if we are using small angle approximation. And how will you relate this angular separation with the linear separation, Saifullah? Is there any relation between this angular separation yn and linear this theta n and linear separation yn? Saifullah.
Can you repeat the question again, sir?
I'm saying, is there any relation between this angular separation and linear separation? We have angular separation, right? I need linear separation. How will you relate it with the linear separation? Saifullah, you have to be regular in class. Huh? Even your class performance are going down. Akshay.
N equal to capital D theta.
Yes. So if small angle approximation is, this is the expression that we have to write. Now, linear separation is D into angular separation. So this will be D into angular separation. But if angle is large and you cannot use angular like the small angle approximation, then what you will do, you have to use this expression tan theta n is y in by d. But in majority of questions of diffraction, small angle approximation is valid. So you can directly use this relation that yn is d theta n. But in cases where this small angle approximation is not valid, you will use this relation tan theta is y by d. This is it. Okay, just note it down. Then we'll do the condition of maxima also. So simple facts, part difference, n lambda, minima, n number of minima. If you have first minima, your n will be 1. For second minima, n will be 2 and so on. If small angle approximation is valid for linear separation, you can just multiply angular separation with d. If it is not valid, then you will use this relation, tan theta is y by d. Any doubt, issue?
सर वो ऊपर नोट लिखना है
नहीं, note नहीं लिखना. Omar, the whole thing, this whole condition for secondary
Yes,
minima.
yes. Yes, sir.
See, what does minima means? Minima means a dark spot. Minima means when light waves and light waves will cancel each other. We did similar thing for interference also. For minima, the condition is part difference should be n lambda. The derivation of this portion is not a part of school syllabus. So I'm not going to derivation part. So if you want minima, you want dark spot, then your part difference should be n lambda. Is this clear, Umar?
Yes, sir.
Next, if you have a sine theta is n lambda, and I ask you to calculate sine theta n, what you will do? You will put this a in the denominator
And lambda by A.
and lambda by. And if I ask you to use small angle approximation, then you can write sine theta equal to theta. So theta n is n lambda by, right?
Yes, sir.
And if I after this angular separation, if I ask you to calculate the linear separation, that all you will do, you will just multiply this angular separation with the d, capital D. What is capital D here, Ishma? What does
Yeah.
capital D here means?
So the distance between the aperture and the screen, no, the slit and the screen.
The slit and the screen is capital D. So if a small angle approximation is valid, then write this expression. If it's not valid, then we use this thing, tan theta is y by d.
Sir, in double slit, the capital D was different, right?
Now, even in double slit, the capital D was the same thing, separation between double slit and screen. A
Okay,
and
sir.
small d was different. Small d was the separation between the two slits.
Sir, can you show the notes, please?
No need to do the notes right now. I'll come to them later. I'll be using that notes part in some conceptual questions. I'll come to those notes later, those notes later part of the lecture. Haji, can I scroll it now? Ishma, Alia, Arpit.
Yes, sir.
1 minute, sir.
Nabil, did you get your marks?
Not yet, sir. I think tomorrow, day after tomorrow, they'll give us.
Anyways, how was your exam? Was it good?
Yes, sir.
Well, paper was very easy.
Yes, sir. Then.
The next is the condition for secondary maxima again. This is the condition for secondary maxima. So again, we need some particular values of part difference for which you will get maxima. And the condition is your part difference should be 2n plus 1 lambda by 2. For secondary maxima, your part difference should be 2n plus 1 lambda by 2 now.
So
This
can you
is-
go for a second, please?
Mhm, mhm.
Done, sir.
Condition for secondary max. So part difference is a sine theta n, or you can write that your part difference is 2n plus 1 lambda by 2. This is the condition. Again, in diffraction, we don't derive this condition. We have derived these type of conditions in interference. Diffraction, those derivations are not a part of this. So sine theta n, and again, if I use small angle approximation, I can write theta n equal to sine theta n, which is 2n plus 1 lambda by 2. This a gets divided here. If I want linear separation, I will just multiply this theta n with capital D, right? So this theta n into capital D. For first maxima, your n will be 1. For second maxima, n equal to 2 and so on. Just note it down. Aji, can I scroll now? Puneet, Akshay, Nabil,
Yes, sir.
Meenakshi. Can I scroll?
Yes, sir.
Everyone are written, na? Up to here?
Yes, sir.
Okay, good. So these are the major relations that we will be using in numericals. So let's start with numerical and then we will come to these conceptual questions later on. Yeah, start with this thing. Note down the question. So this is a formula based thing, just a formula based question. Three thousand. So first minima means first secondary minima. Second maxima means secondary max.
Sir, what is the slit of width?
Slit width is small a. This small a is this, na? Slit of width, sorry. Okay.
Sir, can you show these the conditions for secondary maxima?
Secondary maxima, this is the condition. In diffractions, you will not get very tough type of question. Those questions are in interference. In a syllabus, just have
So you
introduction
can
of
pull a
diffraction.
bit down.
Yes, that's it. There's nothing below it.
Okay.
Written?
Yes.
Okay. Yes. This is the question. 2 mm, 3000 ring strong. D is 8 meter. Just note it down and write your answer in chat room first.
So should we draw the graph?
No need of graph. Right? All these are conceptual things we'll discuss after this numeric. First do this numeric. To draw that graph, part difference, phase difference, conditions of minima and maxima should be very clear in your brain. So first do some numericals, then we will do those conceptual things.
So should we convert Armstrong to meters?
Yes. You have to convert mm into meters and also angstrom to meters. Start writing your answers in chat room. Huh?
Will you stop sharing?
Sorry.
So the question is not visible.
Okay. Answers. Nabil Ahmed. The first part, angular and linear separation. No, Nabil. It's wrong. Akshay, first part is correct. Second part is also correct. Nabil, it's wrong. Just check your calculations again. Akshay is correct. And what about the rest? Saifullah, Hishma, Yashika. Yes, no, both the parts are correct. First is correct, yes. Saifullah, in the first part, where is the angular separation? You just calculate the linear separation of first part. Where is the angular one? You're supposed to calculate both, na, linear and the angular one. In the second part also, you calculate just the linear separation, but it's not correct. It's not correct. Second part, even in second part, the linear separation is not correct. For the first part, the linear is correct. In the first part, your angular separation is missing. In the second part, linear is also wrong and angular is missing. Akshay in the second. No, Akshay, it's wrong. No, Nabil, it's wrong. No, Minashi, wrong. Yashika, your answers. Uneeb, Krishna, Alia. Yes, Alia, both the answers are correct. Good. Yes, Yashika, it's correct. And for the first part, now when you're calculating angle, you're calculating that angle in radians. So write radian also. Huh? Write proper units. Linear is in meters. So write meters. Yashika is correct. What about the rest? Meher, Uneeb. See, this is just a formula based thing, huh? Umar, where is your answer? Gautam Krishna, answers. Meher, Arpit. No, it should not be -7. Just check your powers one again. Saifullah, there is again some issue in the power of 10. Umar, answers.
Sir, I'm trying.
काफी टाइम से ट्राई कर रहे हो. Meher, your answers. तो सीधी सीधी कैलकुलेशन करना थोड़ा ना है कुछ. नंबर रखते चले जाना है, इसमें भी गड़बड़ करोगे. See. Yes, it's correct. See, the first part of the question is asking you to calculate the angular and linear separation of first minima. So use the proper equation for minima, na? For minima, the equation is a sine theta n, right? Is equal to n lambda. Or you can say that sine theta n. Yes, Akshay, it's correct. It's n lambda by a. You need first minima. First minima means n is equal to 1. Put n equal to 1 here. Nabil, check your calculations. Sine theta 1 is lambda by. Substitute values, huh? What is lambda? 3000 angstrom. So that means 3000 into 10 raised to the power minus 10. 3 into 10 raised to power minus 7. A, how much is A? 2 mm. 2 into 10 raised to power minus 3. So when you divide them, you get sine theta 1 is 3 by 2 is 1.5 into 10 raised to the power, it's minus 7 by minus 3, it's minus 4. So you can see this sine theta is very, very small. It's 1.5 into 10 raised to minus 4. So this is the case where small angle approximation is valid. So you can write sine theta 1 as almost equal to theta 1, which is equal to 1.5 into 10 raised to the power minus 4 radian. Now, in this particular case, if you want to use linear separation is theta n multiplied by d. Now, you want to calculate y1. So write the value of y1, theta 1. 1.5 into 10 raised to the power minus 4 into d. How much is d? This is d, 2 meters, just multiplied with 2. So you get 3 into 10 raised to the power minus of 4 meter. Is it clear? Umar, Saifullah, Nabil.
Yes, sir.
Yes, sir.
Okay, in the second part of the question is asking you to calculate the condition for the maxima. For maxima, the condition for part difference is a sine theta n is 2n plus 1 lambda by 2. So you can say that sine theta n is 2n plus 1 lambda by 2a. So you can substitute all values here. Huh? So you need second maxima, means your n is equal to 2. So sine theta 2 is, it's 2n plus 1. So instead of 2, you write 2. 2 into 2 plus 1. It's lambda by 2a. So sine theta 2 is 5 lambda by 2a. So it's 5 lambda is 3 into 10 raised to the power minus 7 over 2a. A is 2 into 10 raised to the power minus 3. So see, it's 15 by 4. How much is 15 by 4? It's 3.75, no? Minus 4. And this is small again, very, very small. 3.75 into 10 power minus 4. You can write sine theta 2 is almost equal to theta 2, which is 3.75 into 10 raised to the power minus 480. And for linear, you can just multiply this angular with the d. Haji, Meher, Uneeb, Saifullah, Umar. Is it clear now?
Yes, sir.
Okay, good. Okay, the next topic. After this, the next is the width of central maxima. See, in interference, we calculate width of all maxima and all minima. But in diffraction, see, the width of maxima decreases. It's not fixed. See, if you look at this picture, this is a real experiment. Huh? So if you look at this diagram very carefully, this is central maxima, it's very wide. Then after central maxima, for other maxima, the width is decreasing. Gradually, the width is decreasing. So in diffraction, the width of all maxima is not fixed. So we don't calculate the width of every maxima. What we do is we calculate the width of central maxima. So we'll be calculating the width of central maxima. And it's a very easy trick to calculate the width of central maxima. The trick says, see, this is central maxima. This much is central maxima. Just after central maxima, you have first minima. Here also, just after central maxima, you have first minima. So if you can calculate the separation between two first minima, you get the width of central maxima. This is a trick that we use to calculate the width of central maxima. So this is central maxima. To the left on central maxima, you have first minima. To the right of central maxima, you have first minima. So the separation between two first minima is the width of central maxima. Yes, clear? This is how we'll calculate the width of central maxima. So to calculate the width of central maxima, okay, well, you can use this diagram. So this is the single slit. This is your central maximum. This is your central maximum. Let me draw it again. This is the slit.
Sir,
Yes.
why does the width decreases as we move away from the center?
We'll come to it. We'll do some
Okay.
conceptual questions where we'll discuss why the width decreases, why the intensity decrease will come. So this is the single slit. This is your screen. And this is the central maximum. This is central maximum. You're supposed to calculate the width of this central maximum. So to calculate the width of central maxima, what we do is we consider this point. This is first minima. And this is also first minima. This is also first minima. So this is the angular separation of first minima, which is theta 1. And this is the angular separation of another first minima, which is theta 1. So if you want to calculate the angular width of central maxima, that will be theta 1 plus theta 1, which is 2 theta 1. If you want linear separation, this is the linear separation of first minima. This is the linear separation of first minima. If you want to calculate the linear width of central maxima, it's y1 plus y1, which is 2y1. So the angular width of central maxima, it is the angular separation between directions of first minima on two sides of central maxima. Means this separation. This separation is the angular width. So angular width is simply 2 theta 1. We know that for minima, we have calculated here also. For the first minima, sine theta 1 is lambda by a. If your angle is small, you can write theta 1 is lambda by a. So it will be just twice of lambda by a. For the linear width, what we will do? Arpit, this is the angular width of central maxima. What you will do to calculate the linear width? Tough question, huh? Arpit, are you in class?
Yes, sir.
Yes, I am saying this is the angular width of central maxima, right? What you will do to get the linear width? Nabil. If you have angular separation and small angle approximation is varied, how you calculate linear separation?
So we multiply by d.
Yeah, we multiplied by d, right? Good idea, good idea. It's multiplied with d. Now we are doing this for quite some time. This is what we did here for from angular to linear. We multiplied by d. Here also we did the same thing. Same thing. Just multiplied with the linear one. Multiplied with the d, capital D. Haji Arpit, clear?
Yes.
Okay. So that is the width of central maxima. Note it down. We'll do one numerical on this concept also. Over, if this is central maxima, what is here just after central maxima? What you have here? This is
First.
max. What first? First maxima or first minima?
It's a minimum. Sorry, maximum.
Yes, Umar, what you're saying? After this central maxima, what is this spot? Maxima or minima?
It's a minimum.
Minima. Similarly here, you have minima.
Before,
So-
right?
Yes. So you have one minima before this central maxima, then one minima, first minima after the central maxima. If you can calculate the separation between these two minima, then that separation would be the width of central maxima, right?
Yes, sir.
So you just have to calculate the position of central minima, first minima. So first minima, what you will use? A sine theta is n lambda, right? This is the condition for central max, first minima. Na?
Yes,
See?
sir.
For minima, we use here also. Na? A sin theta is n lambda. What will be the value of n if I am calling first minima?
1.
1. So put n equal to 1 here. If sin theta will be lambda by. If a small angle approximation is valid, then you can write sin theta equal to theta, right?
Yes, sir.
So it would be lambda by. So if I say that this theta 1 is lambda by a and theta 1 is also lambda by a, so what will be the total angular separation?
2 lambda
Yes,
by
2
2
lambda.
lambda by.
That is the angular separation, right? If you want linear separation, then what we do? For linear separation, we just multiply angular separation with d. So we take angular separation and multiply it with d, with linear separation. Clear?
Yes, sir.
Can I scroll now?
Wait, sir.
Done, sir.
Sir, can you scroll up for a second? Just 1 second. Okay, sir, done.
Can you scroll it if you have written?
1 minute. Yes, sir. Done.
Sir, wait, I'm writing.
Done, sir.
Well, this will be a straightforward thing. If you need width of central maxima, then you use this relation only. Let's do another. Do this one. Double slit experiment means interference. Single slit experiment means diffraction. No, just 1 second. No, not even this. This is also power. Do this one. Single slit means diffraction. Double slit means interference. Young's double slit experiment.
What it is written distance D?
In Young's double slit experiment, distance D between slit S1 and S2 is 1 mm. What would be width of each slit so as to obtain 10 maxima of double slit pattern within central maxima of single slit pattern? Do it.
So what does YDS distance
Ye-
mean?
Young's double slit experiment. In Young's
Okay,
double
sir.
slit experiment, distance D between slits. Okay, let's do this numerical together. So he's saying that in the central maxima of single slit pattern, means in the central maxima of diffraction, you have 10 maxima of double slit, means you have 10 maxima of interference. So this simply means that width of central maxima of diffraction is 10 times bright fringe of interference. Okay. What is the relation for the linear width of central maxima of diffraction? Omar,
What, sir?
what is the expression for the linear width of central maxima of diffraction?
The linear, what?
Linear width for
Uh-huh.
central maxima.
So the linear width of central maxima is 2 lambda capital D by A, I guess.
By and what 10 into and what is the fringe width in interference? We did interference, huh? What was the expression for fringe width in interference?
Sir, right fringe, right?
Hmm.
It was n lambda.
No. Lambda d by d.
Lambda capital D by small d.
Yes. So lambda will cancel this. Lambda capital D will cancel this. Capital D. And you have, if you cross multiply them, you get 2D is equal to 5A. So what is given? This D is given. So your A will be not 5, sorry, 10. 2D is equal to 10. D is given, so your A will be 2D by 10. So your A will be D by 10. H d by 5. So you can substitute the value of d. How much is d? D is 1 mm. So it's 1 mm by 5. So it's 1 by 5. Do it. So it's simply saying in central maximum of diffraction, you have 10 maximum of interference. So width of central maximum of diffraction is 10 times width of central maximum of interference. Aji, written?
Yes, sir. Then.
Okay. So these are the type of numericals that you could get in diffraction. Then there are some conceptual questions. For attempting conceptual questions of diffraction, you should be aware of these facts. We have discussed these facts in interference also, but let's repeat it again. So if you have two waves having a phase difference of pi, if you have two waves having phase difference of pi, then their superposition will be destructive. I'll show it mathematically also, but you should remember. If you have two waves and the phase difference between the two waves is pi, that means if they superimpose, they get subtract out. And if they have equal magnitudes, they will simply cancel out each other. For a phase difference of pi, if you calculate part difference, then your part difference will be lambda by 2. And we have already derived this thing. Like we know the relation between phase difference and part difference. Part difference is lambda by 2 pi multiplied by phase difference. So if phase difference is pi, if pi will cancel out, then part difference will be lambda by 2. So again, I'm saying if you have two waves which have phase difference of pi, then they will get subtracted. This is the case of destructive superposition. But if two waves have phase difference, or the phase difference of pi or the part difference of lambda by 2, they will cancel out each other. So if this is one wave, another wave which have phase difference of exactly pi will look like this. It will look like. So this wave and this wave will cancel each other. Similarly, this wave and this wave will cancel each other. So first note down this thing. No need to draw this whole diagram. We have discussed these things in interference. Just note down this thing. If phase difference is of pi, then destructive. Phase difference of pi means part difference is lambda by 2. All conceptual questions that we will do from now onwards will use this concept. Part difference of lambda by 2 means destructive. Phase difference of pi means destructive superposition. Part difference of lambda by 2 between two waves means destructive superposition. Waves and wave will cancel out.
Should we draw the diagram also?
No need to draw the diagram. Just note down these two facts. We already done this thing in interference, so no need to draw it again. To explain some conceptual questions, this concept should be very clear. Although you have derived this thing in interference, you have derived that for a bright fringe, your part difference should be lambda and n lambda. And for a dark one, your part difference should be 2n plus 1 lambda by 2. Yes, written. Just
One
have
more
to
thing.
write just two statements. If phase difference is pi, that means it's destructive superposition. Phase difference of pi means part difference of lambda by 2, which means destructive superposition. So if you have two waves having phase difference of pi or part difference of lambda by 2, that will mean they superimpose destructive.
So what will be for constructive interference?
For constructive, your phase difference should be 0 or 2 pi. And similarly, your part difference should be lambda. Then you will get construct. Written? Okay, let's scroll it. So the first question, the conceptual question that you can get is explain that corresponding to part difference of n lambda, you have a minimum. This is the condition of minimum, na? Part difference of n lambda. So there's a question in NCERT. Explain. You have to explain qualitatively how part difference of n lambda can correspond to minima. So let's take n equal to 1. When you take n equal to mean 1, that means part difference is lambda. To explain this thing, what you can do is, see, this is your slit, single slit, AB. Slit width is A. Sorry, not A, right. And this is a point P on the screen. To this point P, waves are coming from A and B. Which wave is covering a greater path? Wave from A or wave from B?
B.
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 And the part difference between the waves coming from B and A is lambda. Now what you can do is, you can divide this slit into two parts. So you can consider a point C here. And the waves coming from A and C, what will be the part difference between waves coming from A and C? If the part difference coming in waves coming from A and B is lambda, then what is the part difference in waves coming from A and C? See, if you are dividing the slit into two parts, the part difference will get divided into two parts. So the part difference between waves coming from A and C will be lambda by 2. Similarly, the part difference between waves coming from C and D will also be lambda by 2. So if two waves are coming and they have a part difference of lambda by 2, how will they superimpose? They will superimpose constructively or destructively? Yes,
So constructively, no, sorry, destructively.
destructively. Waves and wave will cancel out each other. That is the reason why you get a minima when the part difference is in lambda. So you can divide this rate into two halves. The part difference between the waves coming from the two halves will be lambda by 2. So they will superimpose destructively. Just take the screenshot of this thing. It's a conceptual question. And if you go through the previous year's questions, the last 5 years, you will find this question. Just take screenshot of it. So the explanation is very simple. You take your slit, you divide your slit into two parts. The waves coming from the two parts will have a part difference of lambda by 2, and they will simply cancel out each other. So there's not much time to write these explanations. Just take screenshot and then you can copy later on. But this is
Sir, I did
something
not understand the question.
the question says, see, we have used this expression, the part difference of n lambda corresponds to a minima, right? This is what we have used in
Yes,
the
sir.
calculations also. The question is, why is that part difference of n lambda corresponds to a minima? So what we do, we take some value of n, let's take n equal to 1. So part difference becomes lambda. And we explain if part difference is lambda, then that will correspond to a minima. How we explain it? We divide the slit into two parts. So we said that the part difference between waves coming from the two parts of slit will be lambda by 2. Because if you take A and B, then the part difference is lambda. If you divide it into two parts, then the part difference between waves coming from the two parts will be lambda by 2. If part difference is lambda by 2, then you will have it.
Sir, can you explain again? I'm sorry.
Okay. So this is the slit. I divide this slit into two parts. If I take this point A and this point B, the waves reaching point P from A and B will have a part difference of lambda. If I divide it into two parts, two equal parts, the first half and the second half, part difference between waves reaching point P from the first half and the second half is lambda by 2. I'm dividing it in two equal parts now. Is it clear? From where does this lambda by 2 come? We just divide this slit into two equal parts. So I'm taking waves which are coming from the first half of the slit and the waves coming from the second half of the slit. So the part difference will get halved. So if part difference is lambda by 2, then lambda by 2 and lambda by 2 is destructive. So wave and wave will cancel out each other. Yes, Umar.
I didn't understood how they are getting destructed.
You understood how the part difference becomes lambda by 2?
Not
See,
really.
so this is a single slit. This is single slit. Waves are reaching from here and from here. And the part difference between this and this is lambda. Fine.
Yes, sir. Fine.
I divide it into two parts. I'm saying what will be the part difference between waves coming from here and here. So you divided the path, so the part difference will become half now. Earlier, you
Yes,
take
sir.
one point here, another point here. Now you're taking 1 point here and another point here. So part difference will become half. And if part difference becomes lambda by 2, then we discussed here. If part difference is lambda by 2, then it means destructive superposition. Yes, Umar.
Yes, sir. Understood.
Similarly, there is another question, like explain why part difference of 2n plus lambda by 2 corresponds to a maxima. Explain a similar question like this thing. We have discussed the part difference of 2n plus 1 lambda by 2 means a maxima. Why is it so? Why 2n plus 1 lambda by 2 results in max? So to explain it, what we do, this is your slit. If I take a point here and I take point here. So let's discuss about the first maxima. For first maxima, n will be equal to 1. If you put n equal to 1 here, then the part difference becomes 3 lambda by 2. So this is your slit, AB. Waves coming from point A and B will have a part difference of 3 lambda by 2. So what I did, I just divide this slit into 3 equal parts. So I divide the part difference 3 lambda by 2 into 3 equal parts, lambda by 2, lambda by 2, lambda by 2. So the waves reaching some point from the first half and the second half will have a part difference of lambda by 2. And part difference of lambda by 2 means they will get cancelled out each other. But this will left, and this will contribute to maximum. This will contribute to central max. So if you look at this thing very carefully, so in central maxima, waves are not getting added up. They are getting cancelled, but 1/3 is left, and that 1/3 corresponds to some intensity. If I ask you to explain the same thing for waves where part difference is 5 lambda by 2. So what you will do, you will divide slit into 5 equal parts. Lambda by 2, lambda by 2, lambda by 2, lambda by 2, and lambda by 2. So this, for the first two parts, the waves will get cancelled out. Next two parts will get cancelled out. Only this part will be left. That's why as you go to the higher order maxima, the intensity will decrease. Here, the 4 by 5 part gets cancelled out. Here, 2/3 gets cancelled out. If you go to higher maxima, then all intensity will get cancelled out. So I explain it again. If part difference is 3 lambda by 2, then what you will do, you will divide your slit into 3 equal parts. From 3 parts, the part difference of the waves is lambda by 2, lambda by 2, and lambda by 2. First lambda by 2 and second lambda by 2 will cancel out each other. Only third will be left, and that third will contribute to the secondary maxima intensity. Just take the screenshot of this also. These questions are important. These are usually asked. This is the reason why as you go to the higher minima, the intensity keeps on decreasing. As compared to first maxima, if you go to fifth maxima, the intensity will decrease. I'll come to it. I'll come to it. Then this is the intensity distribution curve. See, this is the intensity of central maximum. Umar will discuss it at the end of the class. This is the intensity of central maximum. And on the x-axis, you have angular fringe separation. See, for minima, we know that the angular fringe separation is this n lambda. For first minima, it will be lambda, or you can say that sine theta is n lambda by a. For first minima, your n is 1, so it will be lambda by a. For second minima, it will be n will be 2 lambda by a. So at lambda by a, we have first minima. 2 lambda by a, we have second minima. Similarly here, for minus lambda by a, first minima, minus 2 lambda by a, second minima. For maxima, we have this part difference 2n plus 1 lambda by 2. So we put n equal to 1, we get 3 lambda by 2 is the first maxima. Put n equal to 2, you get 5 lambda by 2, that's the second maxima at all. The intensities are for the central maxima, the intensity is maximum. But as you go to higher maxima, the intensity keeps on decreasing. The reason is as you go to higher maxima, the major part of the waves will get cancelled out. So for first maxima, it's I naught, second it's I naught by 21, third it's I naught by 61. So there's no need to calculate from where this number of 21 and 61 came. You have to memorize this. This is the intensity distribution curve. If you can remember the intensity distribution curve of the interference, all maxima will have same intensity. But here the intensity of central bright fringe is maximum and it keeps on decreasing. Decreasing with the order of maximum. Note it down, please. Yes, that is the last topic.
The class is till 10:30.
No. This chapter is over, so I will stop here. The next class will start with ray optics or model physics.
So can we start with ray optics because it is coming in the unit test?
Yes, we can start with ray optics. No issues. Just tell me once you have written. Haji, clear? Written?
1 minute, sir.
After this, there's one homework question.
Sir, can you show the last slide, please?
Mhm.
Done, sir.
Okay, so we'll stop. There's one homework question. Huh? The homework question is, where is the homework question? Differences between minima and maxima. Write 4 differences between interference and diffraction. Note down this question, the homework question. If paper is very easy, you can ask differences between interference and diffraction. Four differences between interference and diffraction. Now the class is over. If you have doubts, we can discuss. So, Omar, now we can discuss your doubts. Those who don't have doubts can leave. Those who have doubts, we can discuss. Yes, Omar, are you there?
Yes, sir, I'm here.
Okay. So let's
Fine,
discuss.
this is-
So your issue was this. So, Omar, if you have, sorry.
So we can say interference takes place only in single slit, diffraction both single and double slit.
Sorry, Naveen, can you repeat?
So we can say that interference takes place only in single slit, whilst the diffraction takes place in both single as well as double slit.
No, interference takes place in double slit. Diffraction takes place in single slit. In fact, if you want to generalize this thing, when you study diffraction, what you do is you divide a slit into a finite number of small slits. When you're saying the single slit experiment, doesn't mean you are taking a single slit. You divide this slit into very, very small slits, and all waves coming from these slits gets interfere, superimpose, and they give a diffraction pattern. While in interference, you have two slits only. You have two sources. The light waves are coming from two sources. So the thing is, you can have interference with two slits only or more than two slits. But for diffraction, you can have diffraction from a single slit as well as multiple slits. For interference, for one slit, you won't have interference. For interference, you need at least two slits. But for diffraction, you can have any number of slits. Umar. So yes, Nabil. Yes, Umar. So if you have two waves which have a part difference of lambda by 2, how will they interfere? Like how will they superimpose? Constructive or destructive, Umar?
So destructive.
Destructive. You have two waves which have a part difference of 3 lambda by 2, right? Divided into 3 parts. So what would be those 3 parts?
So lambda by 2, lambda by 2, lambda by 2.
Okay, for the first 2 parts, the part difference is lambda by 2. So they will superimpose constructively or destructively?
Destructively.
So they will just cancel out each other. So what? So only 1/3 of the part will be left, right?
Yes, sir.
And that is the secondary maximum. So if you have two sources having a part difference of 5 lambda by 2, divided into 5 parts. Okay.
Okay, sir.
So for the 4 parts, will have part difference of lambda by 2 and lambda by 2. They will get cancelled out. Only 1/5 will remain, right?
Yes, sir.
And that will give you maximum.
Okay. Sir, I understood your explanation, but there's a doubt in understanding the question.
Okay. The question simply says if you have part differences 2n plus lambda by 2,